Okay, it's time to start the third talk in this afternoon. It's also the final talk in the afternoon. So I'm very happy to invite Professor Han to give a talk on deep learning for global climate monitoring and predictions. So let's welcome Professor Han.
Thank you very much. So it's great to have an opportunity to have a presentation in ICBS 2024. And also I'd like to thank all the audiences who attended up to the last moment of this week's seminar, the series of the workshop. So today I'd like to talk about the use of the deep learning for the climate change, climate monitoring and predictions. You're familiar with the climate predictions as it is already mentioned several times during the previous talks, but the monitoring so it is a little bit some explanation is required. So I use the term climate monitoring, but it's simply you think it as a data assimilations to see the global feature or to initialize the system. So I'd like to start with one of my papers, which is published in 2019. So it is already 5 years ago. So actually, this published to the Nature, and it's the paper which is acknowledged by as the FSA. So this is written by myself and Jingjia Luo in Louis right now, and Jongwon Kim, who is now a postdoc in the KIST in South Korea. And he's used to be my students as a PhD students. So once this paper is published, it's one of the pioneering study to apply the deep learning for the climate forecast. So at this stage, the use of the deep learning itself. So I'll show you the details later, but the algorithm itself is very simple, but we use the deep learning for the first time to make the global climate forecast, especially for the ENSO, which is this combination of the El Niño and La Niña. So this is the simple schematic diagram of this deep learning system to make a climate forecast. We use the convolutional neural network, and it is good to have some brief explanation of the convolutional neural network during the previous talk, because I can skip how it goes. So it has a convolutional layer and max pooling layer. By repeating this, so we can reduce the dimension of the input 2D, or you can say that it's 3D, because it contains a 2D map of the sea surface temperature and the heat content, which is defined by particularly average temperature from surface to 300 meters from 3 consecutive months. So you can simply think that it's a 3D inputs. So by repeating convolutional neural network, convolution layers and max pooling layers, and it is finally connected to the output variable, which is the Dino 3.4 index, which is the representative index for the El Niño La Niña status for the future time. For example, so as the input is the, let's say the January, February, March of the 1990, then the forecast is the starting from April 1990. So by changing this T here, so the T means the forecast lead month. So so it is changes up to 1 to 23. So by comparing a different combination of the time differences between the input and output variables, we make the forecast very simple statistical based forecast models. So it'd be good to describe in more detail about our deep learning algorithm which is published to 2019. But since then, there have been larger advances by using the most advanced deep learning techniques in our climate or weather communities. So this is the one of papers which is published by Pangu Huawei Cloud, which is named by Pangu Weather. And we saw the presentation about this is also awarded by FSA, and the presentation was in this Wednesday. So you can see that basically the basic structure is quite similar. So once there is an input of various variables for like a temperature, humidity, with different levels, or the surface variable like a surface temperature or surface humidity and surface wind and so on, and make the forecast at the next day. And they use the autoregressive method to make a forecast for the more lead days, to make a forecast up to 14 days. So one of the biggest distinct between my algorithm and their algorithm is to using the most advanced technique, which is referred by vision transformer. So I don't want to explain the details, but in this encoder decoder structures, they use the basically quite different algorithm, which is different from convolutional neural network, which is used by in my studies. And this kind of vision transformer is a big hit, and not only for the weather and climate forecast, but also many domains. So honestly, the convolutional neural network is the out-of-dated deep learning technique these days. And as you saw during the whole week, the vision transformer or graph network is one of the advanced techniques which are widely used these days. So that's why one of this kind of vision of transformer is used very widely, especially these days. And this is also true for the climate forecast to make a temperature forecast or the sea surface temperature over the tropical Pacific. So actually, the Zhou and Zhang 2023 published to the Science of Advance, they also used the vision transformer techniques to make a forecast of the sea surface temperature, two-dimensional sea surface temperature, not only the sea surface temperature, but also other variables which is closely linked to the sea surface temperature at the same time over the tropical Pacific. So they use the multi-head time-space tensions and also the cluster tensions they applied and make the final forecast to make a final two-dimensional outputs. So the question here is that once we use the most advanced techniques, such kind of the vision transformers, so one might think that it really increased our predictability ability of the climate variations. So this is the correlation. The red one is the correlation skill with respect to the forecast lead months. So you can simply think that the correlation skill of 0.5, the threshold for the reliable forecast, then you can simply think that once the correlation skill is above the 0.5, you can think that the correlation is reliable. You can simply think that. So in case of the 3D geoformer, which is developed by Zhou and Zhang 2023, shows the reliable forecast up to 18 months in case of Dino 3.4 and 17 months for Dino 3 indexes. This is for the all-season correlation, so all-season average correlation. So once we separated it for each target month, so it can be for some months, the forecast, reliable forecast can be extended more than 20 months, and some months, for some months, a reliable forecast is obtained only periods of 15 months, lead months. But once we compare this forecast correlation skill with one of my my results, which is basically use the convolutional neural network, which is thought to be very out of dated. Actually, the correlation skill is quite similar. So even though there is some differences, and it's a correlation skill, so it is a correlation skill of Nino 3.4. So you can compare this red line with red line here. So it's even though this is the period to calculate the correlation is a little bit different, but you can roughly compare the correlation skill, which is published in my paper in 2019 and based on the convolutional neural network, and the correlation skill, which is based on the vision transformer and during the much more recent years. So once you put the threshold of the reliable forecast as 0.5, so correlation skill is quite similar, even though there is some differences. So I would say the collision skill will be a little bit better in terms of by using the Bayesian transform, but roughly it's the same. So the point I'd like to emphasize here is that by using the most advanced algorithms is not all we have to do to increase our understanding and predictability of the climate variations. So as a short summary, so I would say that by using the most advanced techniques, deep learning techniques, by adapting the most advanced deep learning techniques is not all, but we have to deal with other much more fundamental problems which we can increase our ability to predict climate variations. So one of the issues I'm now also, for me and our group are now focusing on is to solve some issues caused by quantity and the quality of the training data set. So this is the number of parameters for the many large language models these days. So the number of parameters which have to be trained using sample is 10 million, 100 billion, 10 trillion. So it is increasing tremendously these days. So by using this tremendous number of parameters, the accuracy and the performance of the larger language model is also increasing tremendously. So this kind of achievement, this kind of number of parameters can be successfully trained only by using tremendous number of data sets. In the case of larger language models, so we can do it even as far as we have some money to produce it. So for example, for the large language models, the training sample is kind of the text we are writing or the records we are saying. So that kind of examples, that kind of training data we can generate. So that's why we can deal with such kind of tremendous number of parameters in case of the large language models. But think of it might be also true for the climate or weather forecast or the weather studies. So actually it's not. So once you think the number of observations is in time, so it's in case of it's the number of in situ ocean data per year. So once you take a look at the number of observations per year, so it's increasing not tremendously, but at least linearly. So one can simply think that as the number itself is increasing, so it might be good to have some enough number of data sets, we might think, but actually it's not, because the the meaning of increased number of observation at any particular year is that the observing network becomes much more dense. But the problem is that those those observations obtained from this dense network is not independent from each other. So for example, once you compare the large scale SST variability, which is associated by El Niño and La Niña, the pattern is like this. That means the SST over the Eastern Pacific, tropical Eastern Pacific, and the SST over the tropical Central Pacific moves together. The variation is quite consistent from each other, so that it has very strong autocorrelations. That means by using the observations within this kind of large SST signals, that the observations between those is not independent of each other. So even though we obtain the number of observations by 10, then it is less than 10 as the number of independent samples, as the degree of freedom would be reduced by the large, strong autocorrelation. That means to obtain the large number of independent samples, we should have observed it before the past period, and we never observed it for the future. But you should have observed it from the past long period before, but it is never achieved right now. So what we can observe right now is the present, not the past. So it is already gone period, so we cannot observe the past period. So the number of observations, independent number of training samples we can obtain is quite limited. So it's very different strategy between the large language models and the climate or weather science to tackling this kind of problems. So that I was talked about the quantity of the observations of training data, and right now I'd like to talk about the quality of the training data from now on. So right now, most of the training data set which is used by trained all the data-driven model is obtained from so-called something we call reanalysis. So reanalysis is actually not the observation itself, but it's the mixture between observation and the process-based model by using the technique called data assimilation. So data assimilation is the technique by blending the observations and the process-based model outputs to produce the reanalysis. So in this moment, we have some problem that once the training data set is produced by process-based models, and the reanalysis still contains the systematic bias of the process-based models. So even though we are to produce this reanalysis product, we use the process-based models. So we cannot derive the fully data-driven model. We still need a process-based model because all the training data which is obtained from reanalysis is obtained using the process-based models. So it is quite necessary to replace whole this data assimilation procedure by using process-based model to the deep learning, but this is never achieved before. So to overcome two issues raised by the training data set, the quality and the quantity of the data set, I proposed the two different methods. One of them is a future learning, and the other is the global data assimilation. So the future learning is the techniques I'll explain later in more detail. But the future learning is the technique which can be trained, which can train the deep learning model with a fewer number of samples. So we can deal with so we can hopefully optimally train the deep learning model with a fewer number of samples. That's the techniques. And I'd like to emphasize that until few years before, this future learning is one of the big hits in the machine learning community. But nowadays, nobody are talking about that because so much money is pushed get into the machine learning or AI industry. So getting the number of samples, getting the new training sample is not even a problem for them. So the future learning was something which is very promising for the machine learning community, but nowadays nobody talked about this. So it's very minor area which is now mentioned in the machine learning community. But as I mentioned, as the issue associated with the quantity of the training data set will be there for probably in the era we are living. So the number of this kind of algorithm is quite necessary, especially for our fields. So the other is the global data assimilation, but it is based on the deep learning. So and those two papers, so one of them is now in revision process in MPJ climate, and the second second talk, so it is recently accepted by Nature Machine Intelligence and will be appear next week as online published. So the one of the way of training which is widely used, and also I adapted this kind of transfer learning procedure for my 2019 Nature papers. And so the basic concept of the transfer learning is like this. Once there is a large number of sample pairs, and what we try to do is to try to make system to identify whether the object we are now seeing is apple or not. But unfortunately, there is a small number of samples for the apples. Then we can train the model first with a large number of samples, and the knowledge is transferred to our target task. This is called transfer learning. And practically, this kind of transfer learning is like this. Once we train the model with large number of samples, then the initial weights for each layers just adapted from the previous tasks. Then after that, we did some fine tuning with the samples with the target task, and final model is formulated. That's how the training transfer learning is going on. But the future learning, it is almost equivalent as a meta training is like this. So, this is how the training data is treated for the meta learning or future learning. So it is just adapting the episodic training, which is like the training set is changed every epoch for every episode. So once you take a closer look between the support set and the query set. So query set is kind of target phenomenon we have to predict. So we have to uh, put the labels like test, like a testing. So once you take a closer look between the support set and the query set, and there is no such kind of data set. So there is no class which is contained in the test set in this kind of training set. That means, so we have to predict something. We have to put labels for something which is we never saw before. So there is a dog here. So the model have to predict this is a dog and this is the piano, but there is no labels. So there is one piano, but there is no such kind of labels before. So it's also true for other episodes. So we have the kind of bezels like this, but there's no bezels. Some kind of bezels are here. And by changing this training data set every episodes, so the model, so we want to prevent the overfitting to any particular training data to our deep learning models. So in other words, by changing the training set every time and for every episode, we try to prevent that the deep learning model to prevent the overfitting from any particular training data sets. So this is the basic concept of the future learning or the meta learning. So we adapt that kind of procedure by using applying for the climate forecast. As an example, we apply this algorithm for the winter 2-meter temperature over Korean Peninsula. So the basic the basic structure of the model is quite exactly same as a simple convolutional neural network. So as input, we have the 2-meter temperature, mean sea level pressure, and the meridional wind and upper level zonal wind. And by repeating the convolutional layers, and we try to predict the Korean 2-meter temperature during the DGF season. So the input is the November obtained from November, and the output is from the December, January, February, or just average of 3 months. And the novel approach of this meta-learning algorithm, which is called, there are various meta-learning algorithms or fusion learning algorithms we can adapt, but in this study we adapted model agnostic meta-learning algorithm as a fusion learning. So once there is a losses defined as the difference between predicted temperature and the true temperature, and it is used that information about that loss is backpropagate to update the weights within these convolutional layers. Once it is updated, so it is that model is try to predict our so-called query set. Then we try to predict it, and the loss is backpropagated again to update the model for the support sets. So it's like a so conventional convolutional neural network learning or deep model learning, the whole training data set is defined as one set of the training data set. But in the beta learning or MAML algorithm, we divide the whole training data set into two parts. One of them is the support set and the other is the query set. So we divide the whole training data set into two parts again. And the loss backpropagation is updated independently by accurately predict the support set and query set at the same time. So the updates for the query set is used to update the model for the support set, and supports the model weights for the support set is updated to predict the to accurately predict the query set. The kind of cross procedure of updating the weights in this deep learning model helps the model to avoid the overfitting to any particular training data sets. And the other is the data augmentation we applied. And we know that temperature, Korean temperature and any other temperatures in any other areas is connected to the other larger scale climate variability. In case of the Korean temperature is winter temperature. It is closely linked to the Siberian high index, and also it has some relationship between the El Niño, and it is also associated with the active oscillation. So we use the variation of those variables and defined it as the additional labels, so that the labels we used is not only the Korean temperature, which is the exactly same target variables, but also some other climate variables which is known to be associated with Korean temperatures. So for this kind of data augmentation, we use the other different 7 different indexes which is known to be associated or correlated with Korean temperatures, and we use it as additional labels. So we increase the number of samples by 7 times for the original time series. So what we try to here is that, so this is the experimental design for by applying deep learning algorithm with fusion learning. So MAML is the CNN which is with the fusion learning algorithm, and the CNN baseline is the training process is by using the whole training data set at the same time, and there's no query or support set, and there's no concept of the cross validation or something. So the training data set is from 1950 to 1999, obtained from probably NCEP, but I'm not sure. So, yeah. And the test set data set is from 2000 to 2020, and the month is the input month is November, and output is the subsequent months is like from December to February. And this is the correlation scale of the predicted time series between our reference algorithm and meta learning algorithms. And we obtained the correlation scale between 0.5, 0.6 for the average for 3 months from December to February. And it is significantly higher than our backbone CNN models. And this is not only true for the 3 months average value, but it is also true for individual months, except for the February. So for the February, it is a little bit less than the 95 confidence level, but it is still better, systematically better than the backbone CNN without any meta learning concepts. And as for your information, so once we draw the very similar figure for the process-based model, like a forecast skill of the CMA or the GFDL or GFS from the NCEP, the number is somewhat around here. There's between 0.3 and 0.4. So that's what we are getting. That's what the skill we are getting by using the process-based models. So it's quite similar degree with the deep learning model without any kind of the meta-learning or future learning algorithms. So this is the sensitivity test by using the data augmentation. So red bar is the correlation skill with data augmentation by increasing the labels 7 times by using climate indices, also say with Korean temperature, and the bar with hatchet black red one is the model skill without any data augmentations. So there, even though there is a marginal improvement, but it's also better in some cases, even though some cases it's no big differences. Okay, then let's move on to the next second part of my talk. So it's about the data assimilation. So as you might know, the coverage, global coverage of the in-situ observation is not perfect. So left figure shows the buoy SST observation, and the right panel shows the ship track observations. So by merge, even though we merged all of them, this kind of network is not perfect. Particularly some area over Indian Ocean and some part of the South Pacific and the Southern Atlantic, and even and the Southern Ocean is the most rare, is the region with rare observations. So even though we are increasing the number of observing network tremendously, we cannot cover the whole globe for every time with this observing network. So what we apply to do here to adapt the data assimilation techniques uh, um, using deep learning is the technique called imaging painting. So imaging painting technique is quite well established subject in the computer visions. So once you take the imaging painting techniques with the pictures or the figures with some missing points and missing parts, it can reconstruct the um, the images quite well. So this is the input. So you can simply think that this is the input of the deep learning system, and this is the output of the deep learning system. You can simply think that. So you can see that it reconstructs the images with missing parts quite well. So it can reconstruct very details of the eyes or nose is quite fantastic. So how the model can do such kind of a deep learning model can do such kind of things. So this is technique is so-called partial convolution. So there are several more advanced technique compared to than these partial convolutions to what we used at the same time. So what we try to develop the deep learning model at the beginning. So the partial convolution is one of the best algorithm at that time. So that's why we use the partial convolutions. So partial convolution is the basic concept is quite similar. So once we think that there is a missing parts in the middle of this figure, and what we are doing is that when we use the feature map, which is so we do the single convolutional process, so we can obtain the feature map. The feature map value is obtained only based on the pixels with values, and it is normalized by divided by the number of grid points with values, so that it is normalized. So it is affected by the number. The number is basically does not strongly affected by number of pixels with values. So in this case, so the dot products or element-wise multiplication is applied only these 6 grid points, and is divided by 6, and it gives a feature value of the 5. So we do not use this kind of values of with the missing values. By repeating this procedure, by moving this convolutional filter one by one like a moving window, we can obtain the feature map. So you can do it. So I filled up this number by manually calculating by all this procedure by one. So once we do that, so you can fill those maps. So feature map, which is the output of the convolutional layer, there's no missing values here. So in the input image, so we had the missing value here, and the output of the image, so we don't have the missing value here. So once we upscale this feature map once, then we can obtain the reconstruct image with the same resolutions without any missing values. And the interesting is that once we take a spatial distribution of the value of the feature map, then you can see that relatively higher value is in the middle of the line as along the x-axis, and the values over a large part, the upper part of the lower part is relatively small. And I cannot have time to explain the details, but this kind of spatial distribution of the feature map is strongly associated by the spatial pattern of the convolutional filter. So once the convolutional filter is like this, then the algorithm fill the missing parts with the very similar spatial distribution of the convolution filter. So once you think that the convolution filter is like this slash line, then the feature map value will be high values along this slash line. So I'd like to say that the values or the spatial distribution of the feature map is very strongly follows the spatial distribution of the convolutional filter. And this convolutional filter is learnable parameters. And this is the key, the numbers in the convolutional filter is the key of the performance of the convolutional filter, and it is optimized by successfully reconstructing all the images we are training. So that's why the convolutional filter is trained to reconstruct the training samples without any missing values very successfully. That's how it is trained. So that's what this is the schematic diagram of the deep learning for the global data assimilation, especially for the ocean. So what we did is that the two variables are given as the input of the so-called generator. So it's called generator because it generates new images. So there's two input variables given for the generator, and it gives the output as a reanalysis. And because all the sequential data assimilation getting its inputs sequentially, like autoregressive manners, it is provided as the input of the next subsequent assimilation timescale. It's quite identical to the sequential data assimilation procedures. So once the reanalysis at any particular time is obtained, it is used as with some time integration in case of the process-based models, and it is provided as a short-term forecast and other informations of the at the subsequent data assimilation timescales. By repeating this sequential data assimilation, the model information is all the information is accumulated. So, for example, so once there is so we can simply think that there is an observation in the Eastern Pacific. Then the SST over the Eastern Pacific is updated because we are merging those two information, and the observation is given at this point. And this is by using this input outputs as the input for the subsequent data assimilation timescales, the information of the Eastern Pacific during the previous time frame is accumulated to provide the reanalysis at the subsequent time frame. That's how the observational information is accumulated and make the accurate forecast with the by repeating the data assimilation cycles for several times. And the other concept is the discriminator. So what we used as a generator is generative adversarial network, which is GAN in the short name. So it used the discriminator. So it compares the reanalysis and the ground truth at the same time, and it calculates RMSE, and it is used to train the both generator and discriminator. And we first performed the OC experiments. OC is the so-called perfect model simulation because we don't know the true state for the real world, and that's the one reason we cannot evaluate how accurately the data assimilation is produced in the real world. So what we are doing is that we did the same experiments with the modal world. So for example, we simply assume that long-term integration of the process-based model as a truth. And by adding the random noise, we think it as the observations. So by prescribing the only observation, so the model, the deep learning model never knows the truth, what the truth is. The only information the model is provided is the true plus random error, the value, the random error added value to the true states. So after running the data assimilation for the whole period from 1974 to 2014, so which is a 40-year period, then the model we evaluate the RMSE by comparing this reanalysis field and the true state. We never the deep learning is never seen before. So the red one is the RMSE for the location for the observed locations, and the blue one is the other deep learning algorithm which is proposed before. So, and the black line is the prescribed amplitude of the observed error. So without any assimilation, on the accuracy we are getting by obtaining observation directly is the accuracy, is this degree of accuracy. And by assimilating this information, so within the data assimilation system, we can achieve the reduction of the RMSE about 40 something percent. So it becomes much more accurate by using the observation itself. And it is also true for the global average RMSE. So the result is quite consistent. Because the OC experiments is some kind of emulation in the perfect model. So the real observation is never used, but the observation in the OC experiments was the random error added model simulation. So now, as I showed that the deep learning algorithm is successfully applied for the OC experiments in the real, so we try to apply it for the real world. So the period for assimilating the real observation is from 1980 and 2020, and 1 year spin-up time. So what we've shown as a result is a result from 1981. So variable is the only ocean temperature, which is has a spatial, not only the horizontal distribution but also vertical distribution. So it's a 3-dimensional ocean temperature we use as variables. So simulation frequency is the pentad, and all the observation, in situ observation, what we use is listed as before, and also we use the SST observation here. And this is the red one is the global mean time series, and for the SST and ocean heat content. And so I don't want to time for explain the details, but we also measure the uncertainty of the model. So there is uncertainty which is used to be high because a relatively smaller number of observations, but as the number of observations is increased, the uncertainty is reduced. So it is quite plausible and reasonable. So it is all, and the other line is the reanalysis product from other state-of-the-art centers. And this is a collision scale of the 300-meter temperature, which we try to see the subsurface temperature is as the collision scale of the EN 4.2.4, 4.2.2, and this collision scale is comparable to other state-of-the-art reanalysis products. And this is also for the equatorial temperature to see the evolution of El Niño and La Niña, and it is the reference data, and this is our reanalysis product, and it is almost identical in the area of with sufficient number of observations. For example, tropical Atlantics. So this is a summary. So I will stop here. Thank you very much.
Thank you. So, any questions?
Thanks for the wonderful talk. So I'm just trying to understand that technique when you call it
Fuchsia learning.
few shot, and it sounds like a poor man's strategy if you don't have enough money. Yeah. So I was trying to understand why that helps, and my thinking at the moment is that it's because you try to using the information from neighborhood.
Right. So yeah, it might be right in some aspect. So this is the whole training data set.
Right.
So typically the training is by putting all this training data set and make the predicted labels and calculate the loss at once, and it's back propagated, and all the information is updated based on the loss based on the whole data training data set once. But in this case, because we use the same training data set at the same all the time for the whole training process, so it might be possible that the model is overfitted to any particular training data set. But here we divide the whole training data set into two parts. So one of them is support set, and the other is the query set. And we try to make a forecast and update our model only subset of the whole training data set. And this kind of training data set it differs every episode. That makes the model in this kind of training strategy. So the model is not overfitted to any specific data set. So it is, as the training data set is changed every time, every epochs or the episodes. That's the key.
Okay, so that's where you are kind of avoid overfitting,
right.
And also to make sure that the model is not oversensitive to some
any particular training data set.
But do you have a condition that because you are splitting the data into two parts?
Right.
Is there a risk also that you
right.
So
As
that's how you achieve a kind of right balance.
Right. So that's kind of the knowledge with the domains. So what we did, so actually we did some sensitivity tests, but what we hear is that we divide the supports. So there is the whole data set of the 50 years. So in this case, so the support set and query set is the portion is the 8:2 in this case. So, and we use the whole 50 years, so none of the data is excluded in any case of the training procedures in our cases. So in the ideal case of the fuchsia learning, so even though we have the whole data set, we have to select a subset, and some of the data is excluded from the training period for any episodes. But in our case, we use the whole data set, but it is only divided by a certain ratio. And some of them is treated as the support set, and some of them is treated as a query set. So the only difference from typical training procedure from ours is that we divide the whole training data set into two parts, and it is changed randomly.
Do you have a feeling about is there an optimal ratio to divide it to?
For that, we did some sensitivity tests, but we concluded that the result is that it's not as sensitive to the number, the ratio we are dividing. So any samples which is not included in the support set is included in the query set. We are not excluded any samples in our case. So just a grouping, the different grouping we are making.
Yeah. Smart way. Thanks.
Hi, I have a question about the uncertainty quantification.
Oh, sure.
So the ocean heat content.
Right.
So how do you quantify this spread? this uncertainty range. Does
Yeah.
it include the observational data sets uncertainty itself?
Yeah. So there's a trick actually. so I would say this is not exactly quantify the uncertainty of our reanalysis. So the degree of this uncertainty, we control it by, so we use the technique so-called dropout. So this is other deep learning technique. So the ratio of the dropout is increased, we can artificially increase this uncertainty. So we can control this number of uncertainty, but by changing the dropout ratio. But the dropout ratio, so we determine the drop. So the key is to determine the dropout ratio, dropout rates. So we fix it as a certain number, and this is basically based on the based on the OC experiments. So once we do, so there is the difference between the true state hour and the reanalysis products, and it can be measured exactly in the OC experiments. And the intermodal differences, or the differences between simulation to simulation by adapting the dropout ratio is measured, and we compare those two numbers. So, so you can simply think that so dropout rate is the key to determine this uncertainty, and this is determined by the RMSE of the OC experience, where we know the exact error amplitude. So yeah.
I mean for the data assimilation, for example, we have the the original measurement errors playing a role in the final product, right? So a lot of measurements and representation errors in the observations. So I think I mean the machine learning techniques are. Is there a better way to accommodate or include this information, which make it more data assimilation like?
Yeah, that's a very good question. So this is something we cannot, we couldn't do. So in our system, we cannot prescribe some information about the observational error in our system, in our current system. So that's the way we have to move forward. Yeah.
Thank you.
Any other questions? If there is no other questions, then we will conclude this session. And thanks for Professor Ham's talk again. Yeah.
Thank you.